I recently made a video about biogeochemistry and what it is, what it means, and why it's so important. But I still haven't quite explained what the biogeochemical cycles are and how they work and what drives them, what factors affect them, and how perturbations in these cycles have led to global climate change and mass extinctions throughout Earth's history. So first, to recap what we talked about in the last video over biogeochemistry, we introduced the idea of biogeochemical cycles as basically the transfer of essential elements between Earth's life, air, water, and rocks and soil. So the transfer of elements through different Earth systems. And the importance of these cycles is that they maintain global nutrient balance and sustain life and ecosystems on Earth. And we also mentioned in that video that the CHNOPS elements are typically what we're referring to when we're talking about the elements involved in biogeochemical cycles. The CHNOPS elements are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And the reason we focus on these when it comes to biogeochemistry and these cycles is because these are bioessential elements. In other words, they're essential for life on Earth. And other elements that we talk about also cycle through these systems, but because they're not essential for life, they're more so geochemical cycling rather than biogeochemically cycling like these bioessential elements are. I should disclaim here, though, there are many other bioessential and important elements for life out there, like trace elements, for example, iron, but most of the times we're talking about these major bioessential elements like the CHNOPS and not trace metals, but those are also important and have their own respective biogeochemical cycles. But for this video specifically, we will be focusing on the CHNOPS elements, which cycle through air, the atmosphere, oceans and lakes and other water bodies, the hydrosphere, glaciers and ice, the cryosphere, life, the biosphere, and rocks and soil, the geosphere. These spheres, per se, are what we call chemical reservoirs. In other words, they hold a bunch of chemicals, like there's a bunch of chemicals in the atmosphere and the ocean and rocks and life, like ourselves, and these are the reservoirs for the chemicals in these cycles. And then the other things involved in these cycles are the processes of transferring of elements between those spheres, if you will. For example, as we breathe in oxygen and breathe out carbon dioxide, we're causing this process of transfer of oxygen to us and carbon dioxide away from us, from the biosphere to the atmosphere. And that's the process, and our bodies and the atmosphere are the chemical reservoirs involved with that process. So we will now go over each of these cycles in detail, starting with the carbon cycle. So what drives the carbon cycle? Well, I'm sure you've heard of photosynthesis and respiration. As I just mentioned, we breathe in oxygen and breathe out carbon dioxide. The reason we do this is because our metabolism, the way that we gain energy as humans and all animals, is oxygen respiration. Through oxygen respiration, what we do is we breathe in oxygen and we use that oxygen to oxidize reduced organic carbon. Oxidizing and reducing just means transfer of electrons. We oxidize organic carbon basically by using oxygen to take electrons from it. So we're taking electrons away from the organic carbon, and that converts it into carbon dioxide, which we then breathe out. And this carbon dioxide then comes in handy for photosynthesizing organisms like trees and other plants, which take up carbon dioxide, water, and obviously use light, convert it to chemical energy, and thereby producing oxygen and again organic carbon, or their biomass, which is made up of organic carbon. So because of this photosynthesis and respiration cycle, plants and animals largely drive the carbon cycle. Plants sequester carbon dioxide while animals release carbon dioxide. But it's not quite this simple. See, plants also respire part of the time. So not only do they take up carbon dioxide and release oxygen, they also do what we do. They take up oxygen and release carbon dioxide at night when there's no sun available to photosynthesize. So they're not always sequestering carbon 100% of the time. However, the net effect of photosynthesis by plants is still carbon sequestration because they use the carbon that they take up during the day when the sun is out to produce biomass, or their bodies, their leaves, their tree trunks, their everything about them. And that stores the carbon as reduced organic carbon and therefore decreases the overall amount of carbon dioxide in the atmosphere. However, although plants sequester carbon from the atmosphere, they don't store it long term. Actually, the soil that they live in does. So what do we mean by this? Well, plants take up the carbon dioxide and convert it to organic carbon, making their bodies or biomass. But they're temporary. When plants die, much of that organic carbon is decomposed and converted back to CO2. Soil, however, can store the organic carbon long term, or much longer term than the plant can. This is because soil microbes break down dead plant matter, dead organic carbon from the plant, into much more resistant organic molecules that make up what we call the humus layer or topsoil layer, which stores organic carbon and therefore carbon long term in a form that is not atmospheric carbon dioxide. The same concept applies to marine algae and ocean sediment. So like on land, where plants take up atmospheric carbon dioxide and convert it into biomass, which gets stored in soil, in the oceans, algal blooms, algae, take up carbon dioxide to photosynthesize, convert it to their biomass, their little microbial or algal bodies, which then gets stored in marine sediment when their dead bodies fall to the seafloor in what we optimistically call marine snow. However, carbon dioxide and organic carbon molecules like glucose aren't the only forms of carbon involved in the carbon cycle, obviously. There's also methane, which is another big one that you've probably heard of, which can be produced by methanogens. Methanogens are microbes that use CO2 to produce methane. Methanotrophs use methane to produce CO2. And these are also present in the marine carbon cycle and contribute to maintaining the balance of the cycle. Methane and CO2 play important roles in Earth's atmosphere as greenhouse gases. Now, you've probably heard a lot of bad things about the greenhouse effect or greenhouse gases, but honestly, the greenhouse effect on Earth is essential for life on Earth. It's only bad or harmful when it really gets out of control at a rapid rate, or the CO2 and methane concentrations in the atmosphere increase or decrease really rapidly, because then it can cause temperature changes that are very rapid, and that's hard for life because life takes millions of years to adapt and evolve. So these rapid changes are difficult and have often caused mass extinctions. However, in general, the greenhouse gas effect, if well balanced and only changing somewhat gradually rather than rapidly, is incredibly important and essential for life on Earth and is not a bad thing. It's only bad when it gets out of control. So in summary for the carbon cycle, photosynthesis, carbon sequestration by plants and algae and storage in soil and sediment, and respiration, release of carbon by animals and other microbial decomposers, control the carbon cycle. But not alone. There are other outside factors that also affect the carbon cycle. For example, volcanoes. Volcanoes burn and oxidize and release a lot of carbon, typically carbon dioxide, into the atmosphere. Impacts can also cause the release of carbon into the atmosphere by impacting and burning and oxidizing carbon deposits. And because these impacts typically induce a lot of really hot conditions at the surface in the vicinity of the impact, which induces a lot of wildfires, which obviously are burning and oxidizing and releasing carbon from the plant matter. The melting of ice also releases carbon. So when, for example, there's been major volcanism in Earth's history that's caused global warming due to CO2 release, it can cause what's called a positive feedback loop, or an exacerbating effect, in which ice melts because global warming, and then the ice melting also releases carbon because frozen hydrates or permafrost can contain methane, which when melted releases the methane to the atmosphere, and that is also a greenhouse gas. Burning fossil fuels also releases carbon by oxidizing and burning organic carbon deposits, but there are also processes that sequester carbon, such as photosynthesis and soil and marine sediment storage of carbon, but also an increase in continental weathering rates often leads to an increase in carbon burial, so sequestration and storage, because continental weathering leads to the transfer of ions to the ocean, which might induce calcium carbonate or limestone formation, a carbon-containing rock, in the shallow seas, which would take up and bury the carbon, long-term storing it in the rocks. And then also this transfer of ions to the ocean from weathering increases algal bloom activity because it transfers things like phosphorus and nitrogen nutrients to the algal blooms, which then bloom more, expand, and cause more dead bodies to rain down and bury carbon in the marine sediment. So obviously within that process, I just mentioned carbonate rock formation, such as calcium carbonate or limestone, causes the storage of carbon, and glacier and ice formation. For example, the freezing of methane hydrates or permafrost can store carbon as well. These factors can throw the carbon cycle out of balance. For example, major volcanism, like I'm talking not like a volcano, I'm talking like a huge volcanic field that erupted for like 1 million years, has caused major global warming in Earth's past and subsequent extinction events. For example, the mass extinction at the end of the Permian around 250 million years ago, which was triggered in part by major volcanism. And large impacts have also caused major global warming and extinction events. For example, the extinction of the dinosaurs or non-avian dinosaurs at the end of the Cretaceous 65 million years ago. And rapidly increasing continental weathering rates have caused the other end of the spectrum, or rapid global cooling and glaciation due to carbon burial, and thus decreasing greenhouse gas concentrations, which has also led to major mass extinctions in Earth's past, for example, the Ordovician and Devonian mass extinctions. And now today, we also see the carbon cycle being thrown off of balance because burning fossil fuels is causing major and rapid carbon release, which is similar to the major volcanism or major impact that caused the Permian or Cretaceous mass extinction. But I'm planning to talk more about this in a future carbon cycle video, so look forward to more of that later. Now, moving on to the remaining cycles. Within the remaining CHNOPS cycles, I'm skipping hydrogen and oxygen because those are typically combined into like the water cycle. And we kind of talked about oxygen already within, discussion of the carbon cycle, because oxygen and carbon are largely tied together because of the photosynthesis respiration relationship. So now for the remaining cycles, we have the nitrogen, phosphorus, and sulfur cycles, which are largely dependent on microbes instead of plants and animals like the carbon cycle. Well, not instead, I should say first and foremost dependent on microbes and also dependent on plants and animals, but not to quite as large a degree. Why? Because microbes like bacteria, archaea, fungi, and protists, which are present in nearly every habitat on Earth, produce bioessential compounds necessary for higher life. So what does that mean? Well, let me start with the nitrogen cycle because I think this one perfectly emphasizes the importance of microbes. So nitrogen, in the form of into nitrogen gas, makes up nearly 80% of Earth's modern atmosphere. But we, animals, do not breathe in or take up nitrogen from the atmosphere directly. And if plants don't do that either, how do we then get our nitrogen? How do the plants get their nitrogen? Nitrogen is one of the bioessential elements. So how do we get it? Well, this is where nitrogen-fixing bacteria come into play. These are bacteria that convert atmospheric nitrogen into nitrogen compounds that plants and other microbes can use. There are also what we call nitrifying bacteria that then convert the ammonium that nitrogen-fixing bacteria produce into nitrite and nitrate and other nitrogen compounds that plants can take up. And denitrifying bacteria complete the cycle by converting those other nitrogen compounds back into atmospheric nitrogen. So these microbes make nitrogen available for higher life, like plants, which then take up the dissolved nitrogen, either as nitrate or ammonium typically, through their roots. And then animals like ourselves can eat the plants or eat things that eat the plants to get our nitrogen. And nitrogen cycling not only takes place in soils, but also in the oceans and lakes in their water and sediment columns. Life needs nitrogen in order to synthesize or produce proteins and nucleic acids like DNA and RNA. So without bacteria that fix nitrogen or convert atmospheric nitrogen into usable nitrogen or usable by other life, plants and animals, at least as we know them today, would have never evolved. So now on to the sulfur cycle. Sulfur is primarily stored in the lithosphere or geosphere, rocks. And it's typically stored within minerals like pyrite, gypsum, anhydrite, galena, and sphalerite. And processes that drive this sulfur cycling include volcanism, impacts, and burning fossil fuels, like we talked about before with the carbon cycle. It's a very similar thing for the sulfur cycle. All of these processes release sulfur to the atmosphere. Weathering, like I talked about earlier with the carbon cycle, also sequesters not only carbon, but also sulfur. Sulfur mineral formation stores sulfur long-term in the rock record, and microbes transform sulfur to allow availability for higher life. Again, just like with the nitrogen cycle. These microbes include things like sulfate-reducing bacteria, or SRB, which converts sulfate into hydrogen sulfide, and sulfur-oxidizing bacteria, which convert hydrogen sulfide to elemental sulfur and sulfate, completing the cycle. Some of these sulfur-oxidizing bacteria use a process called anoxygenic photosynthesis to produce sulfur. In other words, instead of producing oxygen through photosynthesis, these photosynthesizing organisms produce sulfur by splitting H2S instead of H2O. How cool is that? And on a separate note, a lot of them use different pigments to absorb different wavelengths of light than oxygenic photosynthesizers do. And for that reason, sometimes they appear purple in color instead of green like oxygenic photosynthesizers. And I talk more about that in my When Earth Was Purple video, which I'll link to the top right. If you haven't seen it, that's like my favorite video on my channel. Thus, similar with the nitrogen cycle, in the sulfur cycle, microbes regulate sulfate availability for plants, which are then eaten by animals. And sulfur is essential for life in that it's used as a key component for many enzymes, amino acids, and nucleic acids. But before we move on to the phosphorus cycle, I do want to make a note about the sulfur cycle that the microbes involved in transforming sulfate to sulfide are anaerobic. In other words, they grow in the absence of oxygen. They actually don't like oxygen to be present at all. And for this reason, the sulfur cycle is closely tied to the carbon and oxygen cycles. So like we talked about earlier, the carbon and oxygen cycles are tied together because of the photosynthesis, respiration cycle, and relationship there. And because the sulfur cycle is tied to oxygen availability, this leads to this relationship where when oxygen is low or depleted or completely absent from, for example, water columns in the ocean or sediment pore waters in the ocean or lakes, for example, the sulfur that is present is predominantly reduced hydrogen sulfide, whereas when things are very oxic or there's a lot of dissolved oxygen in the water column or pore waters, the sulfur compound present is typically more oxidized, either elemental sulfur or sulfate. Therefore, in anoxic zones or oxygen-free zones of the ocean, sulfide becomes abundant, making conditions even worse for animals because one, obviously, when ocean water becomes anoxic, it's hard for animals to breathe in it because animals like fish and coral and all those things, they need oxygen to live, to breathe. They're animals, they respire oxygen. But also, sulfide is toxic to most animals. So the fact that oxygen is gone, so they're literally suffocating, and then sulfide is abundant, it just makes things really horrible for animals in the ocean when it's anoxic. But to these anaerobic bacteria, they love it. They thrive. So when we see periods in Earth's history that the oceans have become largely anoxic, or the deep oceans at least, we call these ocean anoxic events. And these events are typically tied to mass extinctions because obviously, like I just said, they're very harmful to animal life in the ocean. And during ocean anoxic events in Earth's past, we also see that marine sulfide levels greatly increase, causing even more devastation. And I'll talk in future videos much more about OAEs, specific ocean anoxic events. For example, when they occurred, what caused them, the impacts they had on life and climate, and how that info can help us mitigate modern ocean oxygen depletion. And finally, moving to the phosphorus cycle. Phosphorus is crucial for the formation of DNA, RNA, and ATP. If you've taken any biology class, you know ATP is the energy of life. It is so important. It is how we get our energy. And because of phosphorus's incredible importance, but also somewhat difficulty in its availability to life, it is often the limiting nutrient in many ecosystems, hence its use in fertilizer. It's limiting in its availability because it's also, like the sulfur, primarily stored in the lithosphere or rocks, and typically in minerals like apatite. Apatite, as you can see, has many chemical formulas depending on the situation, but it always contains phosphate. And if you'd like a sample of an apatite mineral, just take out one of your teeth and put it on your rock shelf. Now, processes that drive the phosphorus cycle include weathering. Again, continental weathering sequesters carbon like we talked about, and sulfur, nitrogen, and phosphorus. And phosphorus mineral formation stores carbon, again making it limiting. But the good news is microbes have the ability to both sequester and release phosphorus, releasing it and making it available for other life forms. Microbes drive the phosphorus cycle by breaking down organic compounds and releasing phosphate ions. These ions can then be taken up by plants and other organisms for growth and energy production. And some fungi and bacteria also increase phosphorus availability kind of indirectly by promoting plant root growth. In other words, basically, it decreases the amount that phosphorus is limited to plant uptake because an increase in the surface area in which the roots can take up phosphorus ultimately increases the amount of phosphorus that will be taken up by the plant and therefore the plant's growth. This microbial cycling of phosphorus in soils allows plants to take up phosphorus, and animals then get their phosphorus from the plants. But phosphorus cycling also takes place in the ocean, like all the other cycles we've talked about. Marine phosphorus cycling starts with the delivery of dissolved phosphorus from rivers, which then microbes in the ocean can use and transform the phosphorus, working it into the food chain. Because phosphorus is such a limiting nutrient, when its concentration in marine systems is increased due to increasing continental weathering rates, this can cause major algal blooms. For example, dust blown from the Sahara Desert fertilizes the ocean, causing algal blooms due to its phosphorus, nitrogen, and iron content. Such algal blooms can increase carbon burial rates due to the increased biomass production. In other words, the phosphorus allows higher rates of photosynthesis in algal blooms, which takes up carbon dioxide from the atmosphere, incorporates it into the algal biomass or bodies, which then eventually die and fall to the seafloor and become buried. For this reason, purposeful ocean fertilization with phosphorus, nitrogen, and other major nutrients has been proposed as a way to mitigate climate change because it increases carbon sequestration and burial and thus storage of the carbon long term in the marine sediment, taking it out of the atmosphere and therefore decreasing the greenhouse effect and inducing a cooling trend that would balance out the warming. However, I talk much more about this and the potential consequences, which turn out to be really terrifying, in my ocean fertilization video, which I will link up to the top right for you. I highly recommend you check that one out. That's also another favorite of mine. Because these cycles are so interconnected, perturbation in one of the cycles alters all of the cycles. And perturbations in the carbon cycle have the strongest effect and most rapid effect on global climate due to carbon's major role in the atmosphere as a greenhouse gas. As discussed earlier, humans are one of those kind of outside factors other than photosynthesis and respiration that can impact the carbon cycle, kind of like a volcano. But burning fossil fuels is not the only way that humans are impacting the carbon cycle, as shown by these other examples of ways that we're impacting the carbon cycle on the slide here. The effects of these things, like burning fossil fuels, desertification of soils, wildfires, deforestation, and pollution, are increasing CO2 and causing warming. But by understanding the biogeochemical cycles better, we can really work to balance our impact on the carbon cycle and global climate. So I hope you enjoyed learning about the biogeochemical cycles today and how they work and the factors that affect them. And I don't know about you, but learning about biogeochemistry and biogeochemical cycles really kind of solidified for me the fact that Earth systems are so intertwined, and it made Earth science just so much more interesting to me, as well as everyday things. I just go around every day and I'm like, that's going to cause this, which is going to cause this, which is going to cause... It's just so cool to be able to recognize and identify those chain reaction type things happening in nature. And I hope that you kind of gained the same or a similar realization and recognition and appreciation that I have for Earth systems and their interconnectedness from learning about this biogeochemical stuff. You know, nobody asked for this video. I'm making this to kill two birds with one stone because I'm teaching a class largely related to biogeochemistry this semester. So I hope you enjoy it. It honestly is one of my favorite aspects of earth science. And yeah, I guess I will see you guys in my next video. Thank you so much for watching. And I don't know when this is going to come out. I think it's going to be after the holidays, but for me right now, it's like December 20th. So happy holidays. And I hope you all had a wonderful winter break. Bye.